In today's video, we're going to test some of the most popular kinds of wire splicing that I see. This is for smaller gauge wire. In today's test, we will be using 18 gauge. So what I have here is I have a butt connector, a push-in connector, a T-tap, what's referred to as a quick splice connector. I have the standard electrical twist caps. I have a quick disconnect splice type. I'm going to try two methods of using the low temperature solder seal butt connectors. I also have a Wago connector, and then finally I'm going to try just standard splices and test their resistance. So to do this testing, you'll see I have made similar lengths. It's not all identical. I did eyeball this of wires with terminals on the end. You may ask, why not just test the wire? Why put on a ring connector? And that's because I find I get more consistent results with my meter if I have, I can see exactly the spot where I'm crimping it to and, make sure that I do it the same both times. We are using a meter that's capable of reading down to a single micro ohm, so this can check literally up to 1/1,000,000th of an ohm of DC resistance. So to make sure that I do everything evenly, I am going to be using just some quick splices, and I find these are really effective, especially on the type of wire I'm using. Has a cutter with it, and we're not going to be removing any strands. Since we are comparing these, we want everything to be as even as possible. Other precautions I've taken is, you'll likely see, I am wearing nitrile gloves. That is because I don't want any of the oils from my skin getting on the connection and that skewing the results. So I am taking steps to eliminate any external variables. That way each of these connectors gets, a fair shake, and we make sure that our results are as good as possible. Okay, so the first step we have is to measure the resistance of our wire. That way we have our base value, and when we splice it, we'll know exactly how much it has increased. Okay, so it looks like about 7.732 was the lowest I saw there. Okay, so now I'm going to cut this wire. And strip some of this insulation off. And now, to use this, we're just going to make sure, you're supposed to do one side at a time. I'm actually going to give the wires a small twist to make sure it's grouped together well. Then you insert the wire. And use your crimper on that half. Make sure it's nice and tight. Okay, it is. And then do the same for the other half. And then crimp this side. Okay, our connection feels solid. Now I'm going to go ahead and measure this again. Looks like we're right about 8.09. Okay, so on that test we went up about 0.36 of a milliohm. Next up we have a pushing connector. Looks like about 7.99. Now on this one I'm definitely making sure that it's twisted tightly because these typically you see used a lot with solid core wire, so just want to make sure I'm not doing it a disservice. Okay. Tightly. Now do it to this side. And that's secure. It's about 13.8. Just dropping. That's because the wires are pushing against it with some resistance. So 13 point, yeah, right in the 13.8 range, but I'm going to retest this because that seems like a very large jump. See if I can get a better result, or if the wires aren't in there well enough. Now I guess if I pull hard enough, I'm going to try to expose a little bit more wire and see if maybe that's the culprit. No, I don't think so. I'm not actually going to strip more of that. I think this should be sufficient. Just making sure it's twisted very tightly. And that doesn't even want to grab in there. Okay, so I'm exposing more wire to hopefully make a better connection. does not want to grab very well. So these are originally meant for solid core wire, so, and it's likely we just don't have enough strength here to actually force this wire in there. Yeah, it's still coming right out. So I'm going to test resistance again, but I don't feel like these should be used for stranded wire. Okay, so this time it's even worse. It's right around 23 milliohms. So it got worse the second time. If anyone knows something I don't, feel free to leave it in the comments, but I mean, right now the best reading we got was going from 8 to almost 14, so almost a 6 milliohm jump, and you can see I try to get them in there, but I can still pull these out fairly easily. It looks like I actually took some of the wire with it that time, so it crimped it hard enough to strip the wire, but it was not making a good connection. So, quick connectors. I'm not even going to leave the wire in there. Next we have a T-tap, and this device clamps down on a wire, and then it connects with a spade connector that pushes in right here. So these are generally used to add a wire if you didn't want to cut a wire in line, but I have seen, and even tonight on my Facebook when I was talking about making this video, talk to people who say they commonly use this to splice wires. So we're going to go ahead and test this and see what results we get. About 7.98, 7.96. You can see even as I move around. So I've been trying to actually sit them down. That way I'm not shaking it. But I guess let's go at 7.9. Yeah. As you can see, it's so sensitive that as the wire settles, if there's tension on it, it does make it reads that the slightest little difference in the grip. So 7.92 looks pretty good on this wire, so 7.92. Okay, we have a good connection. And so now what we're going to do is we're going to clamp this down on the wire. And I guess I didn't even need to twist that really. And then plug it in and then test our resistance. Okay, it has penetrated the wire. Okay, about 8.59. So there we had an increase of 0.67. So quite a bit more than the butt connector. Next we have the quick splice. And again, this is also normally used for having a wire in line and being able to add another wire to that. Gotta measure the resistance. About 7.92. Okay, so on this we don't need to strip any wire ends, actually. What we'll do is we'll make sure that we have this wire inserted, and then this wire is the one that normally goes all the way through, but we're not going to do that. We're just going to put it slightly past where it would bite in to the wire. So right about there. And this just uses the blade that you can see me squeezing down. It actually cuts into both wires. And so the blade becomes the conductor here. So I'm not sure how well this is actually going to be, but we're about to find out. Okay, so nice solid connection. Okay, so it bounced around, and I don't know if it's because of this or what's moving. So that's interesting. When I'm holding this down, though, pushing on that metal piece, it lowers the resistance. Okay, so now they're both angled the same as they were originally, and we're right around, I mean, I'm seeing 10.4 to 10.6. Okay, so next up we have the quick cap connector. Let's get this, measure the resistance. Okay, what I'm doing here, why it might be off camera, is just because I wanted to do it so I could have these clipped without pulling on the ring terminal. So as you can see here, I just actually move this and get it closer. I'm just doing it like that for ease. We have about 7.1, 7.81. And this is another solution that is typically you'll find used with solid core wire. A lot of in-home use. So Okay, so I'm just going to put these together. Well, first I'm going to twist them tightly. And put the two wires together then. And push them into the twist, and then twisting them. It'll actually kind of like lower the twist cap a bit as it grabs onto the wires. Okay, that is a secure connection. Now to measure the resistance. About 7.67. So that actually lowered the resistance. So I'm going to test this again just to verify our results and that I did not get a bad first read. And you see as you pull it out, the wires are twisted together, so pretty well even. They're still pretty secure. So okay, 7.87. Now let's see if the twist cap improves it again. Looks like it's about 7.8. So yeah, we still do have a reduction, and that's likely because by using this method here, we've actually shortened the original wire. So the wire is not as long, and we have overlapping, and if it's a really good and tight connection that's wire on wire, all we've done is, in essence, shorten the length of the wire. Next we have the quick connect, which are basically the spade and the female quick connect terminal. Yep, we'll get the reading first. Okay, right at about 7.77. And I did think it was weird because normally these are red and a lot of times they're color coded, but this was from just a cheap kit at Walmart, and it said on the back that these were 18 gauge. So it's secure. Looks like about 10.1. And to get this to be perfectly still, I'd actually need to turn off the air conditioner, which I'm not going to do, but so we can get a pretty good example of 10.1. So I'm actually going to jump ahead to the Wago connector. This one is another one that I think may be good for very low current applications, but I don't have high hopes just because of the method of connection with this. So about 7.73. Right around at 8.35, it looks like. We're just jumping back up to. So. And that's about 0.62 of an increase. Interestingly, that's right near where the T-tap was at 0.67, so not too far off the results that we've been getting for the other methods of splicing short of the twist cap. Now we have the low temp solder butt connectors, and I'm actually going to try this two ways. If you check out this graphic, here was instructions from one place I looked where it says just to put the wires in. And then here are the instructions from another place I found that specify pulling the wire through and giving it twisting it together and then pulling it back through and then splicing. So we're going to do it both ways. So first, let's get our resistance reading here. Looks like we have about 7.83. Okay, so for the first test, I'm just going to insert the wire from each end and make sure that it overlaps a bit. And then we use a heat gun. And it melts the solder in the middle. I'm not going to close with this so you can see. Now I'll go ahead and test it. So this is another one with direct wire contact where the wire also became shorter, so I'm wondering if it's going to follow the same principle as the wire connector, or the twist cap, sorry. Um, okay, right around 8.3. So no, on this we did not see a decrease. With that, we saw about 0.47 milliohms increased. So now we're going to take this and we are going to do it as the second set of instructions say, which actually mention twisting the wires together before and pulling it back through. So they're soldered together and twisted together. Okay, so about 7.77. Okay, so on these low-temp solder butt connectors, you'll notice one side is generally going to be larger than the other. That is the side that both of the wires will pull through. So I want to insert this from the narrower side, get it pulled through. So with this here, I'm just going to make sure that they're twisted around each other a few times. Okay, now I'm going to pull this back over. Get the solder in the middle. And once again, it's time to use the heat gun. Okay, that's nice and tight now. Okay, so now we're about 7.6. Looks like right in that neighborhood before it starts, kind of jumping back up. So with that, when it was twisted together, we, again, the wire got shorter. In direct contact, twisted tightly together, so that did reduce the overall resistance by about 0.17. Okay, so next up is we're just going to twist the wires together and measure the resistance. Starting off for about 7.9. Okay, what I've seen a lot of people do is just put the wires together and tightly twist them. Then put some electric tape over this. So we started off at 7.9. Let's see where we're at now. Okay, so still right at the 7.9, maybe just a little bit higher than it was. So again, that was with it just twisted together. See, it's nice and tight. The next we have is a Lineman splice, which is somewhat of an industry standard. NASA has some modifications on it where if you wanted to splice to meet NASA standards. There we go. 7.85. Okay, so with a Lineman splice, you don't want to ever overlapping, and you want to fold one half around the lead and the other, with no spaces in between either. So not overlapping, but right next to each other, pretty much wound as tightly as you can around the opposing wire. So if this is done correctly and then soldered, it will be the strongest point of the wire. It'll actually be stronger than the original wiring itself. Okay, so I don't know if you can see, but you can see how the wire is wrapped around itself here. Now let's measure the resistance. Okay, so about 7.3. Well, hold these still. Actually about 6.95, I'm going to say, it looks like. No, 6.93 even. So, looking at these results, you know, if you're not splicing the wire because you need to make it longer, or I suppose even if you are, this is going to be, it looks like the best connection. And this was, I mean, this is like the basis for what NASA uses. So if you want to, you know, splice wires by NASA specifications, this is the fundamental. The main difference is NASA pre-tins the wires, so before they twist them together. But again, you know, that's solid core. It's not going to be very easy to bend with stranded if you do that. But they would put solder on both of these wires beforehand, perform this specific splice, and then they solder it again, making sure that the wire is completely covered and, you know, any gaps in the wire are taken care of. But looking at that, we had a reduction of about 0.9. So again, I think that's largely due to, you know, how much we shortened the wire there, because we did clear about 3/4 of an inch to an inch off either side. So, you know, on a piece that is maybe 6 inches to begin with, this is now 20% shorter. And actually that's, this were, yeah, so I mean that adds up to about how much we're getting per inch of resistance. So largely the splice is not adding any resistance. If anything, there's less resistance right here because the wire is thicker and we have a tight conductor being made. And overall, the length is shorter. So not only do we have, about an inch here, 3/4 of an inch where the wire is thicker than it was, but overall it's also decreased by that length, which is why why I suspect we see such a large difference in the resistance. So in order of best to worst, what we found was the best was the Lineman splice, which explains why if you're joining wires by NASA standards, this is how you do it. The next, it looks like, was, this actually surprised me a bit, the twist cap. But again, the wires in that one are also pretty tightly twisted together thanks to the way that screws on and folds them together. So both of those actually showed a bit of a decrease in resistance. So the next, it looks like, is no, actually, the low-temp solder connector, when we pulled the wire through and twisted it tightly together, did perform a little bit better than the cap and then the cap. So these are the three that actually reduced our overall resistance, and what they have in common is the wire is shorter than what we started with, and the wires are all making physical connection twisted tightly together. So the next we have the wire, where we just kind of twisted it together pretty tightly with no specific splice, just made sure it was very tightly bound. With that, we didn't really read any increase in resistance. So this wire is also shorter than it was, but just twisting the wires together, we were able to get things back to where they were, but we didn't show any reduction in the overall resistance. So next, it looks like we have the butt connector, and this is one of the oldest ways to actually if you're using other than like a direct splice. These are very popular. They're used a lot. If you use the heat shrink ones, they can make you a waterproof connection. Then after that, it looks like the next best was the Wago connection. So those are pretty neat. They're easy. We didn't see too much, about 0.62, so not too bad there at all. After that, here's where things start getting a bit, definitely a bit iffier. Actually, no, I digress. It looks like the T-tap wasn't as bad as I thought it was going to be. And that's here. So again, one of the, what helps it is, I imagine, we do lose just a little bit of wire, not much as far as length goes. But we're adding it here. So with the T-tap, we added about 0.67. But then with the quick connect, and with this we added about 2.24. And so, overall we know that this wire is now longer than we started with because we just have it crimped here and here. So we actually made it longer, and where it is longer are very thin pieces of metal. I should just pull the insulation off there, but these are not thick. It's common you see these on like speaker terminals, which I'm starting to question why they'd want to use these now, but it is what it is. So there we have the quick connect as the next best, and then we have the kind that you just use pliers down and it bites into it, the common to add a wire to an existing wire. With this, we added about 2.48, so almost 2.5 milliohms of resistance. And then, by far the worst that we tested was this push style terminal that, again, I think it's mostly meant for solid core wire because we likely just, couldn't get it pushed in far enough to make it grab. We were able to make a connection, but I mean, even at our best reading on this one, it was, over 5 milliohms of resistance. So I don't recommend these at all. So there's our results. If you have any questions, just let us know in the comment section below. If you feel like I could do anything better here, you want to see it done differently, feel free to let me know. Always looking to, improve on testing. Happy to retest something if someone brings new information to the table. Just let us know.